Yeah, thank you so much. I'm very glad to be on QHack. My name is Robert, and today I'm going to tell you about how powerful is classical AI from the standpoint of quantum AI. This talk would include a series of my previous work, which are listed below. So one of my biggest dreams is that one day humanity would be able to bring forth powerful quantum artificial superintelligence that have capabilities that outperform the combination of all human kinds as well as classical machines. However, as we are just starting to build these rudimentary, noisy intermediate scale quantum devices, it's certain that this journey is going to be long and arduous. Furthermore, even right now, I don't think we have any idea how to bring forth such an entity. However, I believe that there are a series of very basic and fundamental questions that would be very useful in guiding us through these long journey, and they are listed below. So the first question that I think are important is to understand how powerful are classical AI, or more generally, classical learning agent, that perhaps also includes human minds. But not only just understanding how powerful they are, we also wanted to understand what are the mechanisms that make classical AI powerful. After answering the first two questions, we can start diving into the next two. In particular, after understanding these mechanisms, we can start thinking about how should we design quantum AI. Should we retain such mechanism by just keeping them, or should we adapt in some minor fashion, or perhaps these mechanisms just don't fit quantum AI at all, and we should just forget about them? Another very important question is the fourth question. After getting this collection of mechanisms about classical AI, we can start asking what are some new mechanisms that are not available to classical AI and only available to quantum AI. In this talk, I would focus on the first two questions, as my title suggests. And for the next two questions, hopefully for years to come, the audience for this talk, as well as myself and my collaborators, we are going to make some good progress in answering the second two. As a start, in one of our recent results with Google Quantum AI, we have found some new mechanisms that are only available to quantum AI and not to classical AI. So for people that are interested, please be sure to check out Jeremy McLean's talk, which would happen tomorrow at QHack. So now let's get started. So in my definition, when I consider classical AI, what I mean are any entity that receive, process, and store classical information. So classical AI could perform physical measurement to obtain classical data from the physical universe, store this classical data in classical memory, and process them using classical computation. And together, using these information that's processed, the classical AI can make prediction about what is the future or what would happen in different scenarios and so on. On the other hand, I consider quantum AI to be any entity that receive, process, and store quantum information. So instead of performing physical measurements to obtain classical data, I imagine that quantum AI would be able to transduce from quantum sensor to obtain quantum data, which could then be stored in quantum memory and processed using quantum computation. So now in this talk, I will discuss the following two settings. The first setting focuses on learning from data stored in classical bits, and the second setting studies learning from data stored in quantum bits. So let us begin with the first part of the talk. So here, let's consider a very standard supervised learning setting where we have a training data stored in classical bits. Inside the training data, we have a bunch of examples telling us that for each input, here is the corresponding output. So for example, the input could be description of physical systems, and the output could be, let's say, the ground state properties of such physical system. Now, after the classical or quantum AI agent learn from this training data, we will present the AI system with a new input that's not in the training data, perhaps many inputs that's not in the training data. And what the AI system has to do is to make prediction about the output. So for example, a new input could be a new description of a new physical system that's not in the training set, and we would like to predict the ground state property of such physical system. So now after discussing this setting, there's a very, very natural question. Suppose that computing the output from the input is classically hard. That is, for any classical algorithm, computing the output from the input takes a long time, for example, exponential time. Then is it true that classical AI would not be useful? That is, if we apply classical AI to such problem, should we expect that classical AI would also not be able to compute the output from input or predict the output from input efficiently? Intuitively, it seems like the answer is yes, because one may think that classical AI are just a form of classical algorithms. So if classical algorithms have a hard time predicting the output or computing the output, then how would classical AI be more useful? So this is a question that we study in this paper published last year in Nature Communication on the power of data in quantum machine learning. Basically, we showed that in various cases, the answer is actually no. The key idea is that classical AI can actually learn from data. And due to the computational power containing data, classical AI could actually become more powerful than classical algorithm that doesn't learn from data. Here's a more detailed answer that sort of expand upon it. The reason that classical AI could become more powerful is because in classical AI, it gets access to this training data, which you can think of it as a bunch of examples telling you that for this question, for this input, here's the solution, here's the output. And after getting this collection of input-output pairs, when the classical AI wanted to predict the outcome for a new input, all it has to do is to generalize from this training set. So for example, you could try to find patterns inside the training set so that when given a new input, it can use the solution for these existing inputs to find the output for that new input, which can be much, much easier than computing everything from scratch. So for a classical algorithm that doesn't have access to this training data and doesn't learn from the training data, it has to compute everything. So you can think of it as follows, like we wanted to do quantum computing. So now suppose that I give you Nielsen and Sean, and after you read from it and you learn from it, you can now do quantum computing more easily. But if you don't have anything, I just give you the rules of quantum mechanics, and I ask you to figure out all these quantum computing algorithms like Shor's algorithm, all these Grover search. It's going to be very hard. And that's a similar idea that's working here. Basically, data contain computational power that can boost the performance of classical AI. Particularly, the situation is particularly strong when you think of classical AI as learning from data that obtains from physical experiments. So since we know that nature operates quantum mechanically, you can think of nature as a gigantic quantum computer. And when you learn from experiments coming from the physical world, you're essentially gaining data that's being generated by this gigantic quantum computer. And a classical AI that learned from it could become more powerful than a classical algorithm that doesn't learn from the data. So all of these could be made very rigorous, which is done in this paper. In particular, you can apply like complexity theoretic analysis to understand the situation in a rigorous ground. In particular, in our paper, we show essentially the Venn diagram in the left, or also known as the complexity theoretic diagram. So here we have sets representing problems that can be solved in polynomial time under different classes of algorithm. So BPP corresponds to problems that can be solved using polynomial time classical algorithm, and BQP corresponds to problems that can be solved in polynomial time quantum algorithm. And then we have this intermediate class shown as the light blue circle, which corresponds to the problems that can be solved in polynomial time using classical ML algorithm that learn from a polynomial size training data obtained from nature. So here we're assuming that nature operates quantum mechanically. And then we would have this complexity theoretic plots. So what this means is that there are problems that can be solved efficiently using classical ML, but not efficiently using classical algorithm. And this result have two main implications. The first implication is that essentially by learning from data, classical AI could solve challenging quantum many-body problems that could be hard to simulate classically. And another angle to this, so this is more of a positive angle. It means that using classical AI, you can solve some challenging physics or chemistry problem. But another angle to it is that, as you can see, Originally, you might find some problems to be solvable only with quantum computing or quantum AI, but now this result says that by training classical AI from data, it might be able to solve those questions, which means classical AI could potentially eat into problems that are once thought to have quantum advantage. But when you use training data and you consider machine learning algorithm, these advantage might be diminished or they might just be gone. So that's more of a pessimistic view on this result. And to be more concrete, let's consider one of the killer applications of quantum computing, that is predicting ground states. So in this problem, let's say we have a training data consisting of existing material and molecules, as well as their corresponding ground state properties. And now, basically what we want is to have this classical or quantum AI system that could learn from this training data, and given a new input that describes a new material or molecule that's not in the training data, we want the AI system to be able to accurately predict the ground state property. In one of our previous work, provably efficient machine learning for quantum many-body problems, we proved the following three statements. Now, suppose that all of these physical systems that we study belong to the same quantum phase. Then first of all, we could prove the following. We could prove that predicting ground state properties is actually very hard using classical algorithms without data. That's established in proposition 1 of our paper. Here, the statement relies on the following well-established conjecture, that is, NP-complete problems cannot be solved in randomized polynomial time. I think most people would agree on that conjecture. And the result is also quite reasonable. It's that predicting ground state is hard using classical algorithm. That's why we need quantum computers. However, the second statement is one that's surprising. We proved that in theorem 1, we showed that predicting ground state properties actually becomes easy in the sense of it only requires polynomial time using classical AI algorithms trained with data. In order to establish theorem, what we did is we designed a rigorous machine learning algorithm, and then we showed that by training from a polynomial-sized data, it will be able to accurately predict ground state properties for a new physical system that's not in the training set. Together, what these results implies is that there's only a polynomial advantage possible when you use quantum AI trained with data, and that's established in theorem 5 of our paper. That is, there could be no exponential quantum advantage. However, we do want to know that a large polynomial advantage is still possible. So in practice, quantum AI could still be much, much more powerful than classical AI, but the advantage is not exponential. Furthermore, in our paper, we also conducted a series of different numerical experiments on different physical systems to verify the effectiveness of classical ML in this task. Particular here is just one experiment that we did for a two-dimensional antiferromagnetic random Heisenberg model. The right-hand side shows the ground state properties predicted by machine learning model, and the middle figure shows the exact values computed from a very time-consuming DMRG. So here we're using a one-dimensional MPS that is like a snake shape for this 2D system. So running DMRG actually requires a time that scales exponentially in the width of the systems. On the other hand, the machine learning model that we cook up only scales linearly in system size. Like its prediction time, its training time, the number of training data, all scales linearly in the system size. And you can see that using machine learning models, the predicted outcome is not that different from this very time, like this exponential time DMRG algorithm for 2D system. So now, after seeing that classical AI could be more powerful than one thinks and could eat into problems that were thought to be QC exclusive, where should we go from here? What are the next questions that we should strive to answer? So there's many, and they go into different directions. The first one is, can we design better quantum-inspired classical AI for solving physics or chemistry problems? So by taking inspiration from the design of quantum algorithm for solving this question, could we have a more organic way? Could we find some more smarter way to combine them with classical machine learning model that learn from data in order to solve these challenging and important questions? Another question, another direction is the following. So note that in all of these results that we talked about, it's purely classical. We're looking at classical machine learning algorithm. There's nothing quantum about it. You just use classical computer to do everything. And then we have this provable guarantee in predicting ground state and so on. So I think a very natural question that is very well worth study is how can we incorporate NISQ devices in this classical ML algorithms? Basically, the hope is that by combining NISQ devices and these classical ML algorithms, we will be able to cook up some near-term quantum machine learning models that are both provably efficient in the sense of having rigorous guarantee and no weird things such as barren plateau that would destroy the performance. And furthermore, also become more practically useful because we have some quantum component to it. I do believe that having this quantum component would be more useful than just having classical machine learning models. So while there's no exponential advantage, there could still be very large polynomial advantage. And that advantage could translate into practical usefulness. That's the second question, which can be studied through theoretical analysis or numerical study. And finally, another very different direction is the following. So if you look at this complexity theoretic diagram in the top left corner, you can see that quantum computing are still more powerful than classical machine learning with training data. In particular, in our paper, Power of Data in Quantum Machine Learning, we also started looking into this question in understanding where we can see potential advantage. In particular, we would like to understand what are some flowchart. Basically, in the paper, we proposed this flowchart for understanding what are some conditions that's required in order to see advantage. And furthermore, in the paper, we also conducted this numerical study with system size 30 qubits. And we found that when the conditions are actually met, which correspond to this figure shown here, we see that the performance of quantum machine learning model significantly outperformed the best classical machine learning model. So here we're considering the best classical ML from a wide class of common methods that people use, such as random forest, neural network, gradient boosting, support vector machine, etc. And for all of them, we properly tune the hyperparameters over a wide range, and we still see that the quantum machine learning model outperforms classical machine learning models. So I do believe that there are significant potential there, but one should also note that this is just a numerical study. So could there be some highly specialized classical machine learning model that causes the quantum advantage to diminish? It's possible, but maybe there aren't. So I think further study are still required in all of these different directions. So that concludes the first part of the talk on learning from data stored in classical bits. In the second part, I wanted to dive into the setting where we have data stored in qubits. So similar to before, but the only difference is that now the training data is stored in quantum bits. And also the new input that's not in training data could perhaps also store in quantum bits. And the goal of the AI system is, again, to make good prediction. So now it seems natural to ask the following question. In this case, since all the data are stored in qubits, classical AI should not be so powerful, right? Since it's all qubits, so quantum AI should be the right thing to do. How could classical AI still be very powerful in this setting? Again, similar to before, the answer is kind of no. And the reason is because there are efficient randomized measurements that one could perform to convert quantum data into classical data. So in this paper published at Nature Physics 2 years ago on predicting many properties of a quantum system from very few measurements, we proposed this procedure called classical shadow tomography. And we proved that classical machines can actually predict a huge number of properties of a quantum state by using only a logarithmic number of randomized measurements. In particular, one of the more practical scenario is the following, which is called classical shadow based on randomized Pauli measurement. Here, all we do is very simple. Given a quantum state, we randomly measure every qubit in XYZ basis. And now one could show that we can actually construct a succinct classical representation of the quantum state, which we refer to as classical shadow, such that using this succinct classical representation, one could accurately predict a large number of properties about the quantum state. And one could do that using classical computation only. In particular, one could predict, let's say, the expectation value of local observables, two-point correlation functions or k-body correlation functions, entanglement entropy, Hamiltonians, etc. The key idea underlying this classical shadow is that you can think of quantum state as being this high-dimensional object. So in the left-hand side corner, we have this high-dimensional object. And by performing this randomized measurement, we're essentially doing a random projection of this high-dimensional object into classical bitstring. So that's why we call it classical shadow. And by combining this classical shadow, one could get a good sense of what this high-dimensional quantum state looks like. So now using this technique, instead of considering a standard quantum machine learning model where you have the input qubits and you apply some parametrized quantum circuits such as quantum neural network or quantum convolutional neural network to make prediction or to produce the output, we could consider the following. So given this input qubits, we just do randomized measurement on this input qubits to obtain a classical shadow representation, which is just a classical bit strings representing this quantum state. And then we just feed that classical shadow into a classical AI system to make the prediction. While this seems like a much simpler format where the quantum part is significantly minimized, it's actually a pretty powerful paradigm. So again, let us consider another common application of quantum machine learning, that is classifying quantum phases of matter. So in this case, we would have a training data that consists of the known quantum systems and the corresponding phase. Like, is it in a trivial phase? Is it in a topologically ordered phase? Is it in certain SPT phase, like symmetry protected topological phase, etc. And now given a new quantum system, the AI models would like to predict which quantum phase this new quantum system is in. Again, in this paper, Provably Efficient Machine Learning for Quantum Many-Body Problems, we present an efficient classical machine learning algorithm based on randomized measurement and classical shadow tomography that can provably learn to classify a wide range of quantum phases of matter. Particularly, we showed that the training data and computational time both scales only polynomially in number of qubits. Furthermore, this rigorous guarantee applies to a wide range of quantum phases of matter, including 1D Haldane phase, whole conductivity in fermionic system, symmetry-protected topological phases, two-dimensional topologically ordered phase, etc. Showing that by using this efficient classical machine learning model, taking output from randomized measurement, it is able to classify a wide range of quantum phases of matter. In particular, this specific example, 1D Haldane phase, was previously considered to be an application of quantum convolutional neural network. However, here we show that you don't need this complicated convolutional layers. All you need is just do random Pauli measurement, randomly measure each qubit in XYZ basis, and fit it into classical machine learning model, and you get provable guarantee. Furthermore, in our paper, we also conducted numerical experiment to show that this is not just something that's fun for theorists, but in practice, you also see the same effect. So here we consider a bound alternating XXC model with a phase diagram shown here. There are three different phases: trivial, symmetry broken, and topological. In particular, if one looks at this delta equal to 0.5 line, there's actually only two phases: trivial phase and topological phase. And by just taking all these different states, doing randomized measurement to construct a classical representation, one can now use a classical unsupervised machine learning model to learn how many phases and what are the phases. In particular, we consider this proposed classical ML based on classical shadow representation. And we found that here is the output produced by the unsupervised machine learning model without any label training data. Like, we don't tell which state corresponds to which phase. The unsupervised machine learning model could just uncover the underlying number of phases. For example, here there's two phases, so it clustered the phases into two groups, which corresponds to the trivial phase and the topological order phase. On the other hand, when we consider delta equal to 3.0, in this line, there's three different phases in the phase diagram. And when you just apply this unsupervised machine learning model, we see that it can classify it into three different phases correctly. That is the trivial phase, the symmetry broken phase, and the topological phase. And the same result applies to two-dimensional topologically ordered phase. Here we consider the torical ground state subject to different depths of quantum random circuit, and we consider a trivial phase corresponding to product state subject to different depths of quantum random circuit. As the depth increases, the two phases start to collide because there's no separation anymore. So, but when the depth is shallow, there's a clear signature between the two phases. And that's also correctly identified by this classical unsupervised machine learning model. As the depth is short, it correctly identifies the two, but as the depth increases, that start to match up with the codistance, the two phases start to collide, and it's no longer possible to distinguish them because the random quantum circuit just throw away all these topological details. So now, given these results, again, we can see that randomized measurement plus classical AI is pretty powerful. However, another way to view this is you can think of it as a minimal quantum machine learning model. It's not purely classical because there's this randomized measurement part, which is still quantum. So you can, again, think of it as just a type of quantum machine learning model that is minimally quantum and mostly classical. Using this minimal quantum machine learning model, there's actually a wide range of very nice property. The first point, is that it's noise robust. The reason is because when you perform these randomized quantum measurement, you're essentially doing this Turing operation, like in randomized compiling. And then when you do this Turing operation, it will tailor the noise to become much, much simpler. And then you can do some simple error mitigation to mitigate all these errors. And that's being shown in this robust shadow estimation by Chen et al. The second, there's no barren plateau in these kinds of quantum machine learning model, since no quantum neural networks are involved. We just perform randomized quantum measurement, and then we feed the classical data into classical AI. And the third point is that we can equip these kind of quantum machine learning model with strong performance guarantee, such as for classifying quantum phases. We can prove that it can classify a wide range of phases pretty easily. So now there are several questions that hopefully some of the audience will be able to answer them in years to come. The first question is the following. While one may think that these kind of minimal quantum ML model might not provide too much quantum advantage, I do believe that by increasing the complexity of this randomized quantum measurement, this part, we will be able to obtain certain form of quantum advantage. However, understanding this question require substantial theoretical analysis and numerical study. Another interesting question is the following. So how does variational quantum algorithm and quantum neural networks compare to this minimal quantum machine learning model? So as we all know, in QNN, there's problem with noise robustness, there's problem with barren plateau, there's also a problem with performance guarantee. It's pretty hard to prove that it works for certain cases, and oftentimes when we test them, there are some problems that arises from barren plateau and things like that. On the other hand, this minimal quantum machine learning model seems to doesn't have these kind of weird properties. So how does they compare? Are variational quantum algorithm or these quantum neural network more powerful than this minimal quantum machine learning model, and at what cost? Are they useful for certain things that are not useful using these class of machine learning algorithm, or is randomized measurement plus classical AI all we need? Answering this question, I think, would also be very interesting as future works. So now to conclude, basically in this talk, we showed that classical AI can be much stronger than one originally thought due to the following two mechanisms. The first is power of data, that is, there are computational power in data that enhances those who learn from it. And second, there's power in randomized measurement. By just performing randomized measurement on quantum data, it would provide succinct classical representation that allows classical machine to essentially see quantum data and apply classical AI to such problems. However, I do still believe that quantum AI should be more powerful. However, as I have suggested before, many questions await to be answered, both through theoretical analysis and numerical study. And for some of our most recent results, please be sure to check out Jerry McLean's talk, which will happen tomorrow. That's it for my talk. Thank you so much for listening.
Thank you, Robert. That was fantastic. I definitely learned quite a few things that I had questions about. Thank you so much. So let me shoot a question right from the start. In a lot of my work, and all of us working in quantum computing, we have to understand how quantum compares to classical, right? And it can often be frustrating because classical techniques are, of course, fantastic. We've had thousands, millions of people working to develop them for a very long time, right? They're really so it's a very tough contender. However, there are still challenges. There are still bottlenecks. Could you maybe elaborate on what precisely? Because I mean, again, I would interpret some of your work as saying we can leverage a lot of the great properties of classical AI, right? And think differently about the models. So then for me, that raises the question, what are the challenges that classical techniques are still facing? Is there anything from your particular work that has shed light on specific challenges, difficulties, bottlenecks for these models? And do those give any information about the role that quantum can play to potentially address those bottlenecks?
Yeah. So in terms of this randomized measurement, well, it's quite powerful in many regards. Like you can predict all these different properties.
Yep.
There are still a lot of things that it cannot do. And those often stem from things like uncertainty principle or the fact that when you do measurements, it's actually a linear function in your quantum state. So to elaborate on that, so basically when you do this randomized measurement, it could somehow get away with some level of like incompatibility between properties and uncertainty principle. But when you wanted to predict a large number of properties that are highly incompatible to one another, then suddenly uncertainty principle comes in. And actually uncertainty principle only comes in when you consider measurements, when you consider these more classical viewpoint on this quantum system. But when you just take those quantum system and put them in quantum memory and do some quantum data analysis, you can actually get away with uncertainty principle. And then that allows you to predict properties much more efficiently in various cases. And that was sort of the underlying theme that was being explored in this new mechanism that I talked about for quantum AI. So that's, I think, one example where classical could fail quite badly.
I see. And this is at the level of the data itself, not so much the algorithms, but even how we have either access to some form of quantum data, maybe directly states. But then you're saying if you want to then use this approach of classical shadows, then you end up with some limitations that ultimately are linked to things like the uncertainty principle, right?
Yes,
so it's
and
about
not
the
just
data
using
itself.
classical shadow. I think in our proof we showed that actually whenever you do any sorts of measurement procedure, whenever you do physical measurement on systems, you get certain limitation coming from uncertainty principle and so on, like these quantum effects. And that is, I think, is a one direction where quantum could help quite significantly.
Understood. Robert, and a question also on quantum data. I remember Roger Melko, who's one of the speakers, QHack as well, he gave a talk at Vector. And if I remember correctly, they were discussing basically how to train a Boltzmann machine to replicate sampling from some called atoms or something. So really doing like tomography using these models, right? And I remember being puzzled thinking, wait, but like that means you're training some model to sample from some system that we can't simulate. So that should be basically in contradiction to the theorems that we know about collapses of polynomial hierarchies regarding. And so that was the one point where I thought, oh, but that, of course, the catch is that they're training it on data arising from the experiment itself.
That's true. That's
right?
true.
And so, and I see that was like the seed that got planted in my mind, right? So the question for you is a question that I've had for a long time, and I'm curious what your thoughts are. For me, this raises the question. So we understand that there's power to data, right? That's a big theme, I think, of your results. So for me, that raises the question. So what is the most powerful form of data? Like what is the data that we should be mining, that we should be obtaining, that's going to lead to the most impact, right? What are the experiments that we should be building? What are the systems that we should be analyzing that we can leverage the most to unlock that power? It's a tough question, but I'm wondering what your thoughts are.
That's indeed a very interesting question. So we need this data such that the generalization aspect of it is easy. And then the computational aspect of it is hard, which is a little bit tricky because sometimes when you generalize from data, perhaps you are actually learning how to compute and then you just compute it. In that case, such data would not be that powerful. It really has to be this case where all these data kind of like you can build on them, like given the solution to this question, to this input, given a solution to that input, you can combine them in certain way such that you get the solution for a different new input, which is sort of the form of generalization.
Yeah.
It does seem to be quite a challenge to balance. So for example, if you just get data from like some of the hardest tasks that one could run on, let's say, quantum computer, like all these random circuit sampling.
Yeah.
I think for those questions, so there are also questions, and that's why it looks like this. There are also questions where even if you get these training data, generalize from it is still pretty hard. Factoring is one example. So if you wanted to do factoring, given these examples of given this input and what is their factor, it's not going to help, which is immediate, right? Because you can easily generate this training data by just doing the opposite. You just do prime number and multiply together. Now you have training data. So this kind of training data are not going to be useful for classical AI, which means that for these kind of questions, or which means there are some class of problems, when you get training data, it doesn't really help the classical AI. And then you're asking about, so basically we wanted to avoid them. And at the same time, we wanted to have these cases that are still hard to compute. So it's a little bit hard to balance the two, I think. I do find that this example seems quite interesting. So perhaps maybe that's one way to go. Like you just try to figure out, try to do experiments such that you get the ground state properties for many different physical systems. And now I think that would be a powerful collection of experiments. But then you can also ask, then what is the best way to sample it? What are the training data that we should be sampling? I don't think I have a clear answer to it. But I think in order to answer that question, the first question is to understand what are these tasks? What are the problems such that it's hard using classical algorithm without data, but easy using classical AI trained with data coming from, let's say, quantum experiments or more general physical experiments.
So, and the initial clues is that one potential example of that is problems related to ground state energy estimation, but there could be more, and we have to understand it more.
Yes,
fantastic.
I do believe there are more. I think some question related to dynamics, I think might also have this aspect. So I'm also thinking about some other alternative. I do think there are many, but it's just we need to, since I think it's very new, so I think we need to spend some time understanding what are the problems that have this
Agreed.
That could be proved by learning from data.
Yeah, hence my question. Thanks, Robert. I know I put you on the spot with that. Maybe shifting gears a little bit. You mentioned that you, and I'm quoting what you wrote down, you can comfortably stay by yourself in a room for 2 weeks.
Yes.
Right? Which, maybe 2 weeks is a bit of a stretch for me, but I think I know where you're getting from in terms of kind of being comfortable inside your own mind. Can you tell us what that looks like for you? Maybe give us a glimpse into what goes on in your brain in that case. What makes it such that you can be comfortable, right? Is it? Do you find it meditative? Do you kind of go in your mind to different places? I'm just wondering.
Yes, I always felt like when I'm just sitting there and thinking, that's often I felt freer than when I was like walking down the street where I'm actually moving. It just felt like when I'm in my mind, I could jump around much more quicker than when I was really physically moving. So that was sort of, I think, one of the reasons why I felt quite comfortable just staying in the room. And because I was thinking, if I'm not thinking, I would just, I don't know, but I'm typically thinking. So sorry.
You seem to be doing a good job of thinking as well. So then you're like, for you it's an active state, right? So you're like actively thinking, imagining, traveling in your mind rather than being more like an empty mind kind of state. Is that correct?
Yes.
Interesting.
I think it's less of like empty. I'm actually moving around. Sometimes when I keep everything out, I think that's also a very comfortable experience, which is something that arises when you do meditations and things like that. So it's very different. But I think in order to really stay and feel comfortable, I need something that I could keep thinking. I mean, sometimes when you start thinking, you get stuck. You get into like this loop where you feel like, I need to solve this question, but solving that requires this, and then you make it into loop. Then in that case, it's not very comfortable, and I would just drop that. I would just stop thinking about that and try to find something that have more expensive thoughts that one could play around with. So
Nice. Yeah, thanks for sharing that with us. So I have one more question before we go to some questions from the audience.
yeah,
You mentioned, so you live, I guess Caltech is in Pasadena, which is not too far away from Hollywood. I
yes.
heard you shared a story of how you almost became a
Yeah.
Hollywood star as a kid. I was wondering if you could share it with the audience.
Yeah, that was just a fun story. So because I think in the questionnaire there was like this fun fact. So I thought, oh, that's a fun fact. So for that
Mm-hmm.
one, it's like it was actually when I was quite small. It was like in elementary school or like fifth year or sixth year.
Uh-huh.
I was actually I raised up. I mean, I was born in Taiwan. I was stayed
Yeah,
there for many years. I actually just come to Caltech for my PhD. I actually come to America for
your
my
PhD.
PhD. So
Mm-hmm.
before then, I was always in Taiwan, and my English was not very good. So
Mm-hmm.
especially during my elementary school,
Yeah.
but we were just traveling. I was traveling with my parents, and we went for a vacation in Los Angeles. And then I was
Mm-hmm.
walking down the street in Hollywood, and there was like some scouts for like child star perhaps, and
Yeah, yeah, yeah.
they saw, I don't know, I might be just wandering around, and um, I think it was she asked me to go to this um, interview or like this what's that called? I forgot
Like
the
casting, I suppose. Casting,
right.
yeah.
And then I
Like
went there.
an audition.
Yes, audition. Yes,
Yeah, that's the
audition.
word.
So then I went to audition, and then they asked me to kind of like they give me some lines so that I would say, but my English is super bad. I don't really know
Yeah.
some of the words, so I did a really bad job, and then I think it's just like a first round that I got like I wasn't into the second round.
I see. So
But it was
you had the looks though, is what I'm hearing.
perhaps,
Perhaps.
but yeah. So I always blame my English, and I try my best to improve my English. I watch a lot of like YouTube videos, like English videos, and
Nice.
try to improve on that. But I think maybe
That's
it's
great.
also my acting was bad, so I'm not really sure. But it was a very fun experience.
They made a mistake. They missed out on a star, as far as I'm concerned. Thanks, Robert, for sharing that with us. So, some questions from our viewers. This has come from E6 Peters. That may be Evan Peters. Let's see.
Uh-huh.
So, for the classical machine learning algorithm with data from nature, so that kind of idea, right?
Yes.
Um, can you say anything about upper bounds on the amount of data that's required to be provided to the classical algorithm? Can't you just essentially get into the whole of BQP with enough data? So can you comment on
Yeah,
how
yeah.
much data is needed? Yeah.
Yeah, definitely. So actually, when we're talking about like when complexity theories talk about things, in many cases these are, I mean, at least these classes, they're all polynomial. So everything has to be polynomial. Um, the amount of data is polynomial. The amount of time to train on the data is polynomial. The amount of time to predict when after learning should also be polynomial. So when we're considering this plot here, as well as these results stated here, we're considering the training data to be polynomial size. However, of course, we can start asking, what if we have more data? What if we have exponential amount of data? In those kind of setting, so first of all, if you have exponential time of
Mhm.
exponential size data, the training time might also become exponential. And then the prediction time
Yeah.
might also become exponential. So then the algorithm is no longer efficient. So you're not solving it in polynomial time. That could be one. But then maybe one could say, what if I store all these training data in a random access memory, like a RAM, so that I only need to query the training data in order to um, make predictions. So maybe I can just query like randomly and based on, so for example, you can have an input and then I try to query the data based on this input randomly in order to make prediction. I think that's a very interesting setting.
Mm-hmm.
I'm not entirely sure what the power of that would be. Like if you have this random
Okay.
access memory that stores all your training data, which is exponential size, in some sense, it felt to me a little bit closer to all these literature on dequantization, where you have this sample and
Yes.
query
Yes.
oracle. So
Mm-hmm.
maybe there are some relation to that, where you just put this exponential size training data in your classical random access memory, and then maybe you can do something marvelous. I don't believe that it will become BQP though. I think BQP is still stronger. At least that's my belief. But I haven't studied that question in full detail. But that just seems like a very interesting question. And in many cases, we do have RAM, so we can put a huge amount of data into RAM, and
Yeah.
then perhaps perform that. That's a
Yeah,
interesting question.
I'm intrigued too. I hadn't thought of the RAM per se, but it's a great insight, and I see where you're coming from in its relationship to dequantization.
Right.
Maybe at least one more question. Maybe we'll have time for two. So it's a question from S. Duque Mesa, might be Sebastian Duque Mesa. So the question is, so in these models where you have data coming from nature, from experiments and classical AI,
Yes.
where exactly would you say is the overall power coming from? Is it mostly from the data or from the model itself?
Yeah, it's as the title suggests. I would say it's coming from the data. The model itself is just classical algorithm. So if you put in some garbage data or data that are easy to generate, then it's not going to improve it. So when you have a classical AI that learn from data that are very easy to generate using classical computer, such kinds of classical AI are not more powerful than classical algorithm. It must be that this data come from something that's better. So for example, nature operating quantum mechanically and so on. So yeah, I think the short answer is that it comes from data. The model is just classical algorithm. So yes.
But Robert, maybe playing devil's advocate. So couldn't you say the opposite? You might have the best data in the world, and if you throw it to some garbage algorithm, then you're also gonna
That's
get
true.
something out of
Yes.
it.
Yes.
So
You're correct. So yeah, it should be both. You should have a good model that could really utilize this data in a good way. Like for example, you can think of a model where it's just finding one algorithm such that it fits the input output relation rather than sort of like utilizing in this like a generalization format.
yeah,
More precise way to say that is like you really have to be like the algorithm has to like not like replicate the entire process of generating input output, because if that's the case, then this
it's a
AI
table. Yeah.
algorithm becomes the same as just some classical algorithm. Hope
Mm-hmm.
that was sort of clear from a high level. But
Mm-hmm.
then so this model really have to be sort of taking this data and combining them and then generating the output based on this data. So yeah, so having a good model is also very important that could really utilize the power in data. Um, but the true power actually come from data.
Okay.
But having a good model is important. If you just have a bad model, then that's not going to help at all. So yeah.
Okay. I'm convinced. I'm persuaded. Okay, I'm just gonna go one more question. One more question. I think could you maybe quickly talk a bit more about why is it that classical shadow tomography can help with error mitigation? You mentioned this work.
Ah,
Yeah,
yeah.
maybe in a
So
minute or so.
yeah, that's an interesting. So okay, so for example, if you just consider some noisy computational basis measurement that one cook up, there could be a lot of weird noise that's happening. Like for example, like I know in Sycamore chip, in Sycamore processor, they
Mm-hmm.
have this bias noise. Like when you measure zero, I think it's one way or the other, but when you measure zero, it's more likely that, or when you measure when the underlying state is one, it's more likely that you get zero. But when it's zero, it's less likely you get one. Like
I see.
the error is biased. And
Yeah.
then there's also correlation. Like there's correlation about how things are and so on. And then there might also be coherent errors when you do measurements. And then there's also errors when you apply gates and so on. However, there's this field called, not field, but like there's this technique, a
Mm-hmm.
full set of technique called randomized compiling, which is like if
Mm-hmm.
you apply random gates, you can actually tailor your noise to be something that's much simpler. For example, to become polychannel, which have
Uh-huh.
much simpler form and doesn't have some coherent effects.
Yeah.
And actually, when you run this randomized algorithm, when you randomly apply gates, you are essentially performing random mice. I mean, you're essentially
Compiler.
performing
Mm-hmm.
random compiling, and then that gives you this noise robustness, touring the noise to be simpler form such that it's very easy to learn, and then you can very easily do noise mitigation. So there's this nice robustness part. And that's one aspect. The second aspect is that this randomized quantum measurement, it's a shallow circuit. It's a depth one circuit. So I think people would believe that when you have a depth one circuit, it's very much noise robust compared to when you have like a very deep
Yeah.
circuit and with long range gates
It's
or
true.
so on.
Yeah, the measurement itself is not that complicated to make. Robert, thank you so much. That's all the time we have for today. It was a fantastic talk. I very much enjoyed discussing with you as well, having a chat. Thank you so much and have a great rest of the day.
Yep. Thank you so much.